Okay, good evening to all. The last class we introduced a linearly independent set and then spanning set. So when we say a set of vectors is to be linearly independent, the only solutions of the vector equation is trivial. So that is, suppose we take v1, v2, etc. vn is a set of vectors is said to be, or we say the set of vectors v1, v2, etc. vn is linearly independent if you consider the vector equation, that is alpha times v1 plus alpha 2 v2 plus etc. plus alpha n vn. If you consider this vector equation has, if this equation has only trivial solution, So trivial solution means what? That is alpha 1 should be equal to 0, alpha 2 0, etc. alpha n equal to 0. If this vector equation alpha 1 v1 plus etc. alpha n vn has only trivial solution, then we say the set v1 v2 etc. vn is linearly independent set. Okay, set of the vector space V. Okay, this is linearly independent. If not, then we say it's linearly dependent. Okay, that means what? At least one non-trivial solution exists, then we say v1, v2, etc. vn is linearly dependent. And then next we discuss what is the spanning set. Suppose suppose S is a subset of a vector space V. Say S span V. When we say a subset S spans V, if we take any element V in V, so if we take for every V in V, V can be written as linear combination of elements from S. That is V equal to alpha 1 sum V1 plus etc. plus alpha m Vm. Okay, where alpha is are varies from the field, and then this V is are in the set S. S contains any elements, maybe finite or infinite or anything. Okay, so any element of V can be written as is a product linear combination of elements of S. Then we say S spans V. Okay, so next we define what is a basis. A subset script B, we take script B. So we say the script collection, script B is a subset of a vector space V, is a basis. When we say a subset is a basis, first one is should be linearly independent. So this collection B is linearly independent set. And then the second one is the script B spans the entire space V. If this is true, then we say the collection is a basis. Now, if you take the standard, if you take Rn, so in Rn, the standard basis is usually we take E1 equal to the first position was 1, others are 0. So that is E1. So E2 means the second position is 1, others are 0. So and so on. En is the except the last position, all others are 0. So that is 0, 0, 0, and then 1. So now we can easily prove that this E1, E2, etc. En is form a basis. We call script B is the vectors E1, E2, etc. En is a basis for Rn. Actually, this basis is called a standard basis. So every vector space there is some standard basis. So for in Rn, the standard basis is standard basis. This is standard basis. Now, if we take set of all polynomials, because set of all polynomials, suppose I fix the degree, set of all polynomials of degree n, at the most n. So usually we call that is Pn. Pn of, if suppose I am writing this notation, Pn of R means what? Set of all polynomials of degree less than or equal to n. All polynomials, the coefficients from the real number are, but the degree is at the most n. So that is set of all a0 plus a1x plus etc. plus an x power n. Okay. where these A's are real numbers and n is a natural number. But n, now if suppose I fix the n, so n is fixed. So set of all polynomials, the degree at the most n. For example, if you take a P3 of R means what? All polynomials of degree at the most 3. That means all polynomials is of the form a0 plus a1x plus a2x square plus a3x cube. So up to degree 3, where a is any real number. Now we can easily show that we can add two polynomials. So how we can add constant term, we can add the x term, we can add the x square term, right? So we can add the polynomials term by term. So therefore, the set of all polynomials of degree n over R with respect to the polynomial addition and then scalar multiplication. So scalar multiplication means what? You have to multiply the alpha to the each term. So with respect to this addition, this form a vector space. So vector space over the real number R, over the field R. So this is very important ring. Sorry, very important vector space, set of all polynomials. Now I fix the degree here. Now what is the basis elements? So if you take 1x, x square, etc. up to x power n. So this form a basis for this Pn of R. Actually, this basis is called standard basis. So in the vector space Pn of R, 1x, because if you take any element, look at this. So if you take any element, we can write a0 into 1, a1 into x. Therefore, using this 1x, x square, x power n, we can express any element, any polynomial, we can express using this vectors 1x, x square, etc., x power n, right? So this is called basis, or sometimes it's a standard basis. This is a standard basis in this vector space Pn of R. So this Pn of R is very important. So set of all polynomials. Okay. Now what about the set of all matrices? Suppose I am taking next example. Suppose I am taking 2 by 2 matrices. Set of all 2 by 2 matrices. Use the notation m of 2 colon R. So this is nothing but collection of all 2 by 2 matrix A, B, C, D, where A, B, C, D are real numbers. So A, B, C, D are real numbers. Now we know how to add two matrices. Suppose we have one matrix A, B, C, D, and then another matrix is X, Y. Suppose we have some X, Y, Z, W. Then now we can add term by term. So A plus X, then B plus Y, C plus Z, D plus W. So this is addition. So what is the scalar multiplication? Suppose you are multiplying alpha scalar to the matrix A, B, C, D means what? You have to multiply term by term. So this is nothing but alpha times A, alpha times B, alpha times C, alpha times D. So this is a scalar multiplication. This is a matrix addition. Therefore, this set M of 2, R with respect to this matrix addition and then scalar multiplication, this is a vector space. So you can take any order. I am taking 2 by 2 matrix. You can take n by n matrix, but it should be a square matrix. So it's a vector space. Vector space over the real field R. Now, what is the basis? So I'm taking so bases are matrices. So I'm taking 1, 0, 0, 0. This is a one vector, and then 0, 1, 0, 0 is another vector. Then 0, 0, 1, 0. This is another vector. And then 0, 0, 0, 1. Now, this form a basis. Actually, this is a standard basis. Standard basis for the set of all 2 by 2 matrices over R. So why? Because if you take any matrix A, B, C, D, we can write linear combination of these matrices. So how we can write? So this equal to A into this first matrix plus B into the second matrix plus C into the third matrix plus D into the last one, 0, 0, 0, 1. So that means what? We can multiply A inside and then sum everything, we will get A, B, C, D. Therefore, any 2-bit matrix A, B, C, D can be written as linear combination of the matrix. So therefore, we call this matrices E11 because usually we take this is A11 entry, this is A12 entry, right? Therefore, here A11 position is non-zero. Therefore, we call this matrices E11. So we call this is E12. This matrix is E1, 2, 1, and this is E2, 2. Okay. Suppose if you take 3 by 3 matrices, so if you take set of all 3 by 3 matrices over R, now what is the basis elements? So it's nothing but, so there will totally we have 3 square, 9 basis elements are there. So that is, if you take the first entry is 1, all others are 0, 0, 0, 0, 0, 0. Similarly, the second entry is 1, all others are 0. Similarly, and so on you can take. So the finally we get 0, 0, 0. The last entry is 1. So usually we call these matrices E11 because the first entry A11 entry is non-zero. Therefore, we call this matrix E11. So this matrix we call E12, and this matrix we call ENN. So this matrix form a basis for set of all 3 by 3 matrices. Okay, the number of elements in the basis is 9. Okay, so therefore we define the dimension is nothing but number of elements in the basis. So these are all, again, this is a very important vector space, set of all matrices, and these are all called the standard basis. So we, but in any vector space we have infinitely many bases, but this is a standard one, special one. Okay, and then if you take set of all polynomials, so 1x, x square, etc., x power 1 is the basis. This is one of the bases, and this is standard basis. Standard base means we usually we use this basis, but there are so many bases are there, but this is a standard one. And in Rn, this E1, E2, etc., En is the standard basis. Now we define what is the dimension of the vector space. In a finite dimensional, the number of elements in the basis we define dimension. So in a finite dimension means what? The number of elements. So we define. So what do you mean by dimension? Dimension of the vector space. So the number of elements in the basis. Number of elements in a basis is called a dimension. Is called a dimension of a vector space. Is called a dimension of the vector space V. And if you take any basis, the number of elements should be same. If you take any two different bases, the number of elements in the basis should be same. Okay, that is very important here. So if you take any basis contain the same number of elements, but not the same elements, same number of elements. Okay. So suppose in a vector space, suppose we have a vector space V, and where there are two bases, we take B, script B, and then script B dash. There are two bases. There are two bases. Then the cardinality of B same as the number of elements in B, number of elements in B dash should be equal. So that is a standard result. And if you take any vector space, it has basis exist. So if you take any vector space, suppose the basis contains only the finite number of elements, we call it a finite dimensional vector space. Suppose the basis contains infinitely many elements, we call the vector space is infinite dimensional vector space. Okay. So a basis contains a finite number of elements, then it's a finite dimensional base. Otherwise, we call infinite dimensional basis. So this Rn, these are all finite dimensional vector space. Because in Rn the number of elements is n, therefore it's a n-dimensional vector space. Rn is a n-dimensional vector space over R. A set of all polynomials. Now look at this. So we are talking about the degree n, but the number of elements is n plus 1. We can add extra 1 because 1, x, etc., x power n. Therefore the dimension of Pn of R is n plus 1. So maybe I can write here. So these three vector spaces are very special one. So now what is that? First one is the dimension of the vector space Rn over R. Usually we take here over R vector field is n. And if we take the set of all polynomials, okay, dimension of this Pn of R, the set of all polynomials of degree less than or equal to R over the n R. This is a vector space over the field R. So what is the dimension of this? N plus 1. So what is the basis? 1, x, etc., x power n. And if we take set of all matrices, what is the dimension of set of all m by n matrices? N by n matrices over the real entry. This form a vector space over the real R. So what is the dimension is n square. This is actually this is n. Therefore, what is it? Each entries have 1. So therefore n square. Okay. So how many entries are there? If you take n by n matrix, how many entries? There are n square entries. Therefore, the dimension is n square. So these three vector space are very important, and the dimension also very important. So similarly, you can define C power n, set of all n tuple over complex number C power n over C is a vector space of dimension n. But if you consider over R, is a dimension 2n. Anyway, we will discuss that later. These three vector space are very important vector space, and the dimensions are n plus 1 n square. Now we give the some characteristics of basis. So basis, if and only if the one of the following is true. It's very important theorem. So basis means what? We have to check two conditions. One is linearly independent and then spanning set. But the theorem says no need to check both the condition. One of the thing we have to check. So the theorem is, so maybe we can state the theorem. Suppose script B is a basis. Script B is a basis for the vector space V. Basis for V. V means is a vector space over some field. Okay. If and only if, this is notation for if and only if both the directions true. If and only if one of the following is true. One of the following, either we can say one of the following is true. So the first one is, this script B is a set, actually is a maximum linearly independent set. That is the maximum linearly independent set. If you add one more element, that is not linearly independent. It should be linearly dependent. So this is the maximum linearly independent set. So to prove script B is a basis, it is enough to show that script B is a maximum linearly independent set or minimum generating set. Script B is the minimum generating set. That means what? If you remove one element, that set cannot generate the whole space. So it's very, very important theorem. So we say a collection script B is a basis if only if one of the following is true. Either that set is maximum linearly independent set or minimum generating set. Okay. That means maximum linearly independent set means what? That is a maximum set. Suppose if you add one more element to the set, that is not linearly independent, should be linearly dependent. Similarly, what is mean by minimum generating set? That is the minimum number of elements should generate the whole set. If you remove one element, that set cannot span the entire set. Okay. For example, in R2, so again, if you take a real number R2, in R2, already we know that E1, E2 is the basis, is the standard basis, right? The basis for R2. Suppose then I am saying that this is the minimum generating set. Suppose you are removing one element, either E1 or E2, this E1 itself cannot generate this R2 because E1 is nothing but 1, 0. So this vector cannot generate all the elements because if you take 0, 1, this is an element in R2, we cannot write this vector is a multiple of scalar multiple of this vector because here the first position is 0, but here the first position. Therefore, if you remove one element, either E2 or E1, that remaining set cannot generate R2. Therefore, minimum we need two vectors to span R2. Therefore, minimum 2. So if you take 3 elements, that is not happen. You can take 3 elements. So for example, instead of taking E1, E2, if you take any 2 elements, should be linearly independent. So for example, suppose I am taking some order pair 1, 1 and then 1, -1. Suppose I am taking these 2 order pair. Now we are going to show that these 2 form a basis. So it is enough to show that either we can use the definition should be linearly independent and then spanning set. So we cannot get this vector 1, -1 by multiplying this vector by scalar. Suppose you multiply some scalar alpha to the first vector, you cannot get the another vector, right? We cannot find any alpha such that alpha times 1 times 1 comma 1 is not equal to 1 comma minus 1. Therefore, these two sets are linearly independent. Linearly dependent means what? Suppose two vectors v and then w, we say these two vectors are linearly dependent if and only if nothing but one can be written as scalar multiple of others. If your one vector can be write as a scalar multiple of other vector, then we say v and w are linearly dependent. Suppose we cannot write one vector as a linear scalar multiple of other vectors, then these two vectors are linearly independent. This is for two vectors. So when we say two vectors are linearly independent, one vectors cannot be write as a scalar multiple of other vectors. So here therefore clearly this 1 comma 1 cannot be 1 comma minus 1 cannot be written as scalar multiple of 1 comma 1. We cannot find any scalar such that the product is equal to 1 comma 1. Therefore this is linearly independent. Independent. Not linearly dependent, therefore it's linearly independent. It's clear. Now this generates. This generates the entire space. That means what? If you give any x comma y, you can write linear combination of these two vectors. If you give any general element x comma y in R2, x comma y can be written as some scalar in times 1 comma 1 plus some other scalar times 1 comma minus 1. So we have to find such an alpha beta such that this is happened. Now how to find this alpha beta? Just to simplify and then sum, what will get alpha plus beta, that is the first coordinate, and then the second coordinate alpha minus beta. So this is equal to x comma y. Therefore we can solve, we have two equations, alpha plus beta equal to x and then alpha minus beta equal to y. Now just to add these two equations, we get 2 alpha equal to x plus y. Therefore alpha equal to x plus y by 2. Now we find the alpha. So such an alpha exists. Similarly, you can find the beta, substitute, otherwise subtract from first equation to second equation, we get a beta value. So usually what you will get beta, just you have to subtract, we get 2 beta equal to therefore x minus y by 2. So therefore such an alpha beta exists. Therefore this x comma y can be written as a linear combination of the vector 1 comma 1, 1 comma minus 1. Suppose you are removing one vector, either 1 comma 1 or 1 comma minus 1. Suppose you are omit or remove one vector. Suppose I am removing this vector. Now the remaining vector 1 comma minus 1 cannot generate the entire space. Why? Because suppose we take this vector, just one vector 1 comma minus 1 spans entire R2. It is happen or not? No, because suppose we take specific element. So what is the specific elements we can take? We can take 0 comma 1. So we cannot write this 0 comma 1 is a scalar multiple of this 1 comma minus 1, because the first entry is here 0. Therefore we have to choose alpha should be 0, but the second coordinate here non-zero. So this single vectors cannot span entire space R2. Therefore minimum we need 2 vectors to span the R2. Therefore this is the basis. Even you can take 3 vectors, 4 vectors, but minimum we need 2 vectors to span R2. But if you take suppose 1 comma 1, 2 comma 1, that is not a same vector. So that is suppose you are taking 1 comma 1 and then 2 comma 2. These are 2 different vectors, but these 2 vectors cannot span entire space because these 2 are linearly dependent. Because this vector or this vector can be written as scalar multiple of this vector. That is 2 times this, right? 2 times 1 comma 2 is nothing but 2 comma 2. So therefore these 2 vectors cannot span the entire space. Again, this is not linearly dependent because one vector is a scalar multiple of other vectors. But say minimum 2 vectors are there. That is not a guarantee, but if it is basis, it should be minimum. Okay, so it's very important result. Basis if and only if that set should be maximum linearly independent set and then minimum generating set. That means what? Suppose maximum means what? Suppose you are including suppose script B is a basis and should be maximum linearly independent sub. Suppose you are adjoining some element x to this set, then the resulting set B union singleton x is linearly dependent. Script B is the maximum linearly independent set. If you add one more elements, that set becomes linearly dependent. So similarly, suppose script B is a basis. Suppose you are removing one element, either x or something you are removing from the set. This set cannot span. or cannot generate or span the entire set. Generate R2. That is the minimum set to span the entire set. Okay. So suppose if you know the number of elements in the basis, suppose n is the number of elements. So suppose the dimension of that is another one important result. Suppose we know the dimension of the vector space. Suppose n is the dimension, then if we take any linearly independent set of n vectors, that becomes a basis. Okay, suppose a note or remark we can take. Suppose V is a vector space and then dimension of the vector space V is suppose n, then if we take any linearly independent set of n elements, so then any linearly independent set containing n elements, any n elements, but should be linearly independent. So contains n elements or containing n elements is a basis. So any linearly independent set containing n elements is automatically basis provided the dimension of V is n. Okay, similarly, any spanning set containing n elements is a basis. Either you can use linearly independent. So that's the first one. So any linearly independent set containing n elements is the basis provided the dimension of V is n. So that's the first point. Now we take any generating set containing n elements. So any generating set contains n elements is a basis. Okay. So if we take any generating set containing n elements, that become a basis because they given the dimension of V is n. Okay. Now, so maximum we discuss the important theorems. Okay. Now we will discuss find the dimension of some special type of subspace that is very important. If we take singleton zero, because we know that singleton zero always is subspace. So now we write the properties of dimensions. Okay. Properties of dimensions. Okay. So first one is suppose W is a subspace of V. Okay, be a subspace. Then the dimension of W should be less than or equal to dimension of the bigger space V. So if we take any subspace, the dimension of the, because subspace itself is a subspace, is a vector space. Therefore, we can talk about the dimension. So the dimension of the subspace is always less than or equal to dimension of V. If it is finite dimensional, suppose the V is a finite dimensional, there should be strictly less than dimension. Okay. So why I am writing here less than or equal to? Sometimes we get the subspace dimension equal to the bigger space dimension, provided this only happen only in the infinite dimensional vector space, not for finite dimensional vector space. So otherwise we can write here, if V is a finite dimensional vector space, finite dimensional vector space, and W is a subspace, W is a proper subspace, then the dimension of the subspace W strictly less than dimension of V. Suppose dimensions are equal, suppose dimension of the subspace equal to dimension of the whole space V, implies W should be equal to V. Suppose in a finite dimensional vector space, a subspace dimension equal to the bigger space dimension, both are equal. The only possible is the subspace should be equal to the whole space. It's very important. So usually in set theory, in real analysis, how we prove two sets are equal? We prove two containments. Okay. So in real analysis or any mathematics, we usually prove. Suppose we try to prove, if we take in general, suppose we prove two elements A, B equal. So when we say two elements are equal, we have to prove two less than or equal to A should be less than or equal to B, and B less than or equal to A. Then this to happen, we can say if and only if A and B are equal. This is for elements. Two members are equal, then we can prove A less than or equal to B and B less than or equal to A. So for sets, suppose we try to prove two sets A and B are two sets are equal, if only we have to prove two containment. That is, we have to prove A is a subset of B and B is a subset of A. Then we claim that A equal to B. So this is for just sets. But in the vector spaces, when we say two subspaces are equal, then no need to prove two containment. So in a vector space, Vs means for vector space. Suppose two subspaces W1 equal to W2. In the vector space, two subspace W1 equal to W2 if and only if you prove one containment, either W1 is contained in W2 or W2 contained in W1, and then we have to prove dimension should be equal. Dimension of W1 equal to dimension of W2. No need to prove two containment. You have to prove one containment, and then you have to prove that dimension should be equal. Then these two subspace should be equal. This is special property for only for the subspace. No need to prove two containment. You prove one containment, either W1 is contained W2 or W2 contained W1, and then prove that the dimensions are equal. Then from this we can conclude that two subspaces are equal. Okay, so this is very important. So therefore, for finite dimensional vector space, if you take any proper subspace, the dimension of the proper subspace should be less than dimension of B. But if you take infinite dimensional vector space, sometimes the subspace dimension equal to the bigger space dimension. That is very important thing. Okay, now we come to our picture. Suppose if you take any matrix, M by N matrix, then we have a subspace. We can talk about some subspace. Okay, suppose A is an M by N matrix. So A is ABN M by N matrix. So how the matrix look like? Suppose I am taking this A equal to A11 first entry, A12, etc. A1n. That is n column, m rows. A21, etc. A22, etc. A2n, and so on. AM1, AM2, etc. AMN. So if we take any m by n matrix, now look at the columns. So this is the first column. We call capital C1. The first column. This is C2, second column. This is Cn, nth column. Therefore, this C1 can be look as a vector. So what is a vector? We can write A11, comma, A21, comma, etc. AM1. So how many positions are there? There are m position. Therefore, this should be belongs to in Rm. So this column vector is a vector because we can see as a n tuple. So similarly, what is C2 is a second column. We can view as a vector. So that is A12, A22, etc. AM2. So on, the last column we can take Cn is A1n, A2n, etc. AMN. So these are all members of Rn. Now take these vectors C1, C2, etc. Cn, put into a set. Suppose I am taking S equal to the vector, first vector, column vector C1, C2, etc. Cn. Now, so given any set, we can talk about the span of the set. So we take all the possible linear combination of the C1, C2, etc. Cn. So that is span of the set S. That is all possible linear combination alpha 1, C1. CS, C1, C2, Cn's are fixed. Alpha n, Cn. I am varying only the scalars alpha i's from the scalar f. Now clearly this form a subspace. Actually this is called row space. Sorry, column space. So actually we call this column space. columns or column space. Because we are using the columns to generate a subspace, so we call it as column spaces. Instead of taking columns, we can take the rows. Look at the matrix. So this is the first row. So we call this is R1. This is the first row. So this is the second row. And so on. This is the mth row. Now using this R1, R2, because R1 is a one vector, A11, A12, etc., A1n is an element in Rn. Similarly, R2 can be as a n tuple. Similarly, Rm can be as a n tuple. Now using this R1, R2, etc., Rm, now take the linear combination of some scalar, some A1 times R1, first row, some A2 times R2. The linear combination of the columns, rows, how many rows? M rows, Rm. Here R1, R2, Rm is a fixed vector. So we are varying the scalars, all Ai's from the field F. Now this form a subspace. This subspace is called a row space. Okay, row spaces. So row space is a space. So row space is nothing but row space of the matrix is nothing but you take the rows R as a vector and then take the linear combination of the rows. This form a subspace. That subspace is called row space. Column space means what? The columns for generated some subspace. That subspace is called as column space. Okay. Now, and the null space is nothing but the solution of the equation Ax equal to 0. That is null space. Okay. So there are two subspace. Now given single matrix A, so what is the one more subspace? Null space. So what is the null space? So null space is nothing but you are collecting the elements satisfy the condition Ax equal to 0. So therefore should be is an Rn. So therefore given a matrix, we can talk about three subspaces. Suppose suppose A is a m by n matrix, then we have a three subspace. So one subspace is row subspace. Using row and then we span a subspace, we call it a row space. And then using the columns of a matrix, we can generate a subspace. That subspace is called a column space. And then find the solution of the, so collecting the solution of the equation Ax equal to 0, that form is subspace. That subspace is called null space. So now we have a three subspace for a given matrix. That matrix need not be a square matrix. It may be any order. It's a rectangle matrix also. So therefore, given single matrix, we have a three subspace: row space, column space, null space. Now these are all subspace, and we know that any subspace or any vector space, we can talk about the basis. Therefore, we can talk about the basis. Therefore, we can talk about the dimension. So dimension is nothing but number of elements in the basis. So therefore, the dimension of the row space, because row space is subspace, therefore we can talk about the dimension. Okay. So therefore, dimension of the row space we define is a row rank. We define is a row rank. And then the dimension of the column space. Column space is a subspace. We can talk about the dimension. So the dimension of the column space we define column rank. Define, that is the definition for column rank. Okay. And then the dimension of null space we defined as a nullity. So dimension of the null space we define this is nothing but nullity. So already we define what is the rank. Now we define row rank and column rank. Now the important theorem says these three numbers are equal. That is row rank equal to column rank equal to rank. Okay. So that is very, very important result in linear algebra. So what is the result? So maybe we can state as a theorem. So let A be an m by n matrix. Let A be an m by n matrix. Then row rank equal to column rank equal to rank of the matrix. row rank, the number equal to a rank of the matrix, row rank of A. Okay, maybe I can write here because we can form a row space using the rows of A. Okay, so this is equal to row of rank of the matrix, and this is equal to column rank of the matrix A. So row rank of A equal to column rank of A equal to rank of the matrix. So these three numbers are equal. So therefore, finding the rank of the matrix same as finding the row rank of the matrix. So row ranking material, just to take the rows of the matrix is formed by a subspace. So spanning the rows of the matrix is formed, gives the some subspace. So the dimension of the subspace is called the row rank. The dimension of the row space is row rank. Dimension of the column space is column rank. And this the theorem says everything equal and should be equal to rank of the matrix. So this is very important result in linear algebra. So row rank equal to column rank equal to rank of the matrix. So for any doubt? So this result actually regularly they will ask. If you take any competitive examination, indirectly or directly we use this result, row rank equal to column rank equal to this. Okay. So any doubt in this? Okay. No. So next we move to some things. So directly we start the there is some important formula is there. I already said the sum of two subspace is subspace, intersection of two subspace is the subspace, right? Now what is the dimension of the sum of two subspace? Okay, that is a very important result. So I can write here. Suppose W1 or V1. So V1 comma V2 are subspaces of V, or subspaces of the vector space V, then finite dimensional vector space. Then dimension of V1 plus V2. Since V1 is a subspace, V2 is a subspace, therefore sum of two subspace is subspace, therefore we can talk about the dimension. So the dimension of V1 plus V2 equal to dimension of V1 plus dimension of V2 minus dimension of V1 intersection V2, because again V1 intersection V2 is a subspace, therefore we can talk about the dimension. We have to subtract. So usually you are studying the set theory, cardinality of A union B equal to cardinality of A plus cardinality of B minus cardinality of A intersection. The similar thing here. So there are two subspace V1, V2, then dimension of V1 plus V2 equal to dimension of V1 plus dimension of V2 minus dimension of the intersection. Okay, this is very, very important formula. Okay. So next maybe we find some dimension. We solve some problem if possible. Otherwise, okay. Any doubt?
There is any relation between dimension, rank, and trace of a matrix?
Sorry, once again. So dimension,
Dimension, rank, and trace of matrix.
dimension. Yeah, that's what I'm saying. So, yeah. Now we can define the once we define the linear transformation, we define what is the rank is nothing but the dimension of the range space. Dimension of the range space we define rank. So therefore we define what is the linear transformation of that. So once we define what is the linear transformation, using this linear transformation we define what is the rank. Okay. You are asking that one, or so there is a relation between rank and the dimension, right? So the rank is nothing but dimension of the range space. So what is the range means? So first we define what is the linear transformation. So quickly we now I discuss what is the linear transformation. Suppose we have two vector space over the same field. Okay. Suppose V is a vector space. V is a vector space over the field F. We have another vector space W is a vector space over the same field f, then a function t from one vector space V to another vector space V is linear transformation. When we say it's a linear transformation, it's a function, but it satisfies extra condition that. So the first condition t of v1 plus v2 or t of, so first condition is t of, if you take any element here, v1 plus v2 should be satisfy the condition t of v1 plus t of v2. So this is true for every v1, v2 from the domain. Now the second condition is t of some scalar alpha times small v equal to alpha times, if you take, you can take alpha outside, alpha of t of v. So if you take any alpha from the field f and any v in v, if your function satisfies these two properties, then we say t is a linear transformation. Okay. Suppose if you take the domain and the codomains are same vector space, then we say this is a linear operator. So linear operator means what? Domain and codomains should be same vector space. Okay. So that is, so we call this a linear transformation. So transformation means what? Domain and codomains are different vector space. So that is the first definition. Suppose a linear transformation, LT means linear transformation. So T from V to V is called linear operator. Is called linear operator. Okay. If the domain and codomains are same and this is the linear transformation, such a linear transformation we call linear operator. Suppose since f itself is a vector space, if the field itself is a vector space over f, so next definition, a linear transformation T from the vector space over the field f, because this f itself is a vector space over f. So such a linear transformation is called linear functional, is called linear functional. So everything is a linear transformation. The only difference is the codomain. Domain and codomains are same vector space, that we say is a linear operator. If the codomain is a field, then it's a linear functional. Suppose the domain and the codomains are different vector space, such a linear transformation we say it's a linear transformation. So we have to differentiate these names: linear operator, linear transformation, linear functional. Okay. So now, so that means what? We have two vector space V and W. Suppose this is a one vector space V and we have another vector space W. Okay, since it's a vector space, therefore definitely 0 should be there. Okay, suppose we have a function from this to this, we call T is a function. Suppose since V is a vector space, definitely 0 should be there. Again, W is a vector space, therefore the identity should be there. Now we are collecting the elements from the domain which maps to the particular element 0. So we fix 0. So what are the elements here which maps to only that 0? All the elements, we are collecting elements from the domain which maps to only the 0. We call the subset is called kernel of the map T. So therefore, what is a kernel? T is a subset of V. We are collecting elements small v from the domain V such that this V maps to 0. So that is, we are collecting the elements from domain which maps to 0. That collection is called kernel of T. We can easily prove that this kernel is a subspace. Is a subspace of the domain. Okay. So kernel is nothing but we are collecting the elements which maps to 0. Okay. Now what is the range means what? We are collecting the range space. So therefore all the elements from V which maps some elements in the range. Okay. So that is define R of T, sometimes called R of T, or image of T, IM, image of T, or range of T. There are so many names. So range of T is nothing but is of the form T of V. You already studied in the real analysis. So set of all T of V such that V in V. So that is a range space. Okay, now we define this also a subspace. This range is also a subspace of the codomain. So this also a subspace of the codomain W. Now any subspace we can talk about the dimension. Now the dimension of maybe we can remove this. Either take image of T or sometimes called T of V. Okay, T of capital V. So now the dimension of the image of T Im. So image of T, we define rank of T, rank of the operator T. So rank of T is nothing but dimension of the image. Now nullity is nothing but dimension of the kernel. So dimension of the kernel of the map T we define is nullity. Nullity of T. So the theorem says rank plus nullity equal to dimension of the domain. So rank of T is any linear operator, linear transformation. Rank of T plus nullity of T equal to rank a dimension of the domain. Domain of the linear transformation is V. So dimension of V. So this is a rank nullity theorem. So any linear transformation, we have a two subspace. One subspace is image of T, another subspace is kernel of T. So whenever we have a linear transformation, we have a two subspace. One subspace from we get from the domain, another subspace we get in the codomain. Okay. So therefore, the dimension of the range space we define the rank. Dimension of the null space we define kernel or null space. So kernel of T is nothing but null space of T. The dimension of kernel is called nullity. For example, if we take some linear transformation from R2 to R2, we will check first of all is a linear transformation or not, and then we have to find the what is the null space, what is the kernel and all. So exercise. Suppose we have a function T from R3. R3 is a vector space. So M maps to R2. So R3 is a vector space over R. R2 is also a vector space over R. Now I am defining some function T of, so any element in R3 is of the form ordered tuple x comma y comma z. Suppose, but range contains only the ordered pair. Suppose I am defining x comma y goes to x plus y comma z. Suppose I am defining like this. So we have to check is a linear transformation or not. We can easily prove that this is a linear transformation. So first we have to check that 0 maps to 0, 0. So that is first we have to check any linear transformation 0 maps to 0. First we have to check this. So after that we have to check T of x plus y equal to T of x plus T of y. And then T of alpha x equal to alpha times T of x. Okay, first check this one. Second, check the scalar multiplication and T of alpha x equal to alpha times Tx or not. Third, we can check the third T of x plus y equal to T of x plus T of x satisfied or not. Okay. So from first you check 1 and 2, that is enough. Maximum that we can check that the function is linear transformation or not. So now we can easily check that substitute x equal to 0, y equal to 0, z equal to 0, we get 0 plus 0 comma 0 is 0, 0. So therefore 0 goes to 0. And then if you multiply alpha, T of alpha times x comma y comma z equal to alpha x plus alpha y comma alpha z, you can take alpha outside, we get satisfied. Therefore, we can easily check that this is a linear transformation. Now, what is the kernel? Now, what is the kernel of this linear transformation? So, kernel of T. So, kernel of T means what? We are collecting elements from the domain. That means we are collecting the ordered tuple x comma y comma z in the domain R3. What is the condition satisfied? The image of this x comma y comma z, this element should maps to the 0 element in the codomain. So 0 element should be 0 comma 0. So we are collecting the x comma y comma z which maps to 0 0. So what are the elements which maps to 0 0? So that is, so this is collection of all x comma y comma z in R3. What is T of x comma y comma z? We are defining x plus y comma z equal to 0 comma 0. Since these two order spaces are equal, therefore first term equal to first term. Therefore, x plus y equal to 0. and then second we get z equal to 0. Now you have to substitute here. So set of all. So from this first equation x plus y equal to 0, we can write x equal to minus y or y equal to minus x. Or we can write y equal to minus x. Therefore, we don't know about x, but y should be minus x and x should be 0. Okay, it's in R3. So the only unknowns are here x. Therefore, x varies in R. So that means what? You can take x outside, x times 1 comma minus 1 comma 0, such that x in R. So therefore, the kernel contains actually the kernel spans the vector 1 minus 1 0. So only one vector. But any element in the kernel is of the form x minus x 0. This is the kernel of T. Now what is the dimension? So the dimension of the kernel of T is only one, because the only one vector, namely 1 minus 1 0, spans the entire space. Therefore the dimension of the kernel is 1. So what is the basis? The basis is the set only the single element 1 comma minus 1 comma 0. Only this element spans the entire kernel. Because any element in the kernel can be expressly a combination of this 1 minus 1 0. That is a scalar multiple of this one. Therefore the kernel contains only one vector, namely 1 minus 1 0. Now what is the range space? So therefore we have to prove that is it onto or not. Okay. So onto means what? So how we prove a function f from A to B is onto? So when we say the function is onto, if we take any element B in B, we can find a in A which maps to this A B. So such a is exists, then we say the function is onto. If we take any element in the codomain, we can find a element from the domain which maps to the element is onto. Okay, now what is our domain? Domain is R3. Codomain is R2. So we try to prove this function is onto. Therefore, given any element in the codomain. So if we take general element some a comma b. So if we take any a comma b in R2, so what is our aim? Find tuple order tuple x comma y comma z in R3, which maps, that is T of x comma y comma z equal to a comma b. Such a x comma y comma z exist or not, we have to find. Suppose exists, then this is happen. So this implies what is the definition of T of x comma y comma z is nothing but x plus y comma z equal to a comma b. Now we get a two equation, x plus y equal to a and then z equal to b. Okay. Now what we can choose? So we have to find a x, y, z. So therefore we found the last coordinate is always b. So anyway we have to find this x, y, z in terms of ab, because we know ab. So therefore now we find that the last coordinate is b. Now what about the first two coordinates? Suppose if you know, if we take any coordinate x, then the second coordinate should be what is a minus x. You can choose anything, but the sum should be a. Okay. Otherwise, if you fix a minus anything, a minus x means the first coordinate is x. But we need a sum should be x. Therefore, we can always find a number. No need to take x, so we can take some other. But the condition is the sum of first two coordinates should be a. It's always possible. Either you can choose 0 comma a, because the sum is this one. So simply say I can take 0 comma a. These elements maps to a comma b, because by the definition you got to add the first two coordinates and then fix the last two coordinates. Now fix b. Sum of 0 plus a is a. Therefore no need to write now all the things. We have to find at least one tuple x, y, z which maps to a comma b. I can choose either a comma 0 comma b or 0 comma a comma b. There are so many numbers, there are so many vectors which maps to a comma b. So simply I am taking, now I get idea, so directly I can write. So T of, I am taking 0 comma a comma b. This three tuple maps to a comma b. Because of the definition, maps to sum of these two and then the last one. Or either you can choose this vector or you can take a comma 0 comma b. This vector also maps to a comma b. Or there are so many things. Or anyway, what is the condition? The sum of first two coordinates should be a. Now I can take either 1 comma. Suppose I fix 1 here, therefore I can write here a minus 1 comma b. This also maps to a comma b, because the first sum of first two is 1 1 cancel, we get a. Or a minus 1 comma 1 or 2 comma a minus 2. There are so many pre-images. Therefore, this function is onto. So therefore, onto means what? The image of a function should be entire space. So dimension of this nothing but dimension of this R2. So dimension of, we know that R2 is 2. Therefore, rank of T is nothing but dimension of image. But here image is nothing but whole space, that is dimension of R2. But dimension of R2 is 2. Therefore, rank is 2. Already we found that rank nullity is 1. So rank is 2. Therefore, 1 plus 2 is 3. So 3 is nothing but the dimension of the domain. So we know that the dimension of R3 is 3. So given any function, we have to check the function is linear transformation or not. Once you say linear transformation, we can find the kernel and then image. So the dimension of the kernel we call nullity. Dimension of the image, the range space, is called rank. Okay. So whenever you can stop now. Thank you.